Hello, welcome to another module in this massive open online course. So, we have looked at the least norm solution to an underdetermined system of linear equations. In this module, let us look at an interesting application, a very practical application of that in the context of, which is in the context of multi-user beamforming in wireless communication systems, right. So, let us talk about multi-user, or basically what we also call as multi-user beamforming, all right, which is again a very interesting application in the context of this is essentially an application of the least norm in wireless communication. And just to mention this, clarify this, this least norm, this is also sometimes known as the minimum norm, all right. I think both can be used interchangeably, that is the minimum norm solution to a system of linear equation or the least norm solution to a system of linear equations. Okay. And what is this application multi-user beamforming is essentially as follows. So, let us say once again you have multiple antennas and this is your receiver. Let us say you have L antennas and you have users, two users. Now, you have, this is a multi-user scenario. So, you have user 1 who is the desired user and you have user 2 who you can think of. So, this is your desired user and user 2 is the interfering user, and you have a channel between each user and the receiver, right. So, you have the channel, right. So, let us say channel coefficients of the desired user, these are denoted by H1, H2, so on up to HL, and the interfering user we denote by G1 up to GL. So, HI equals the channel coefficient of the desired user, that is between the desired user and antenna I of the receiver, and similarly Gi is the channel coefficient between the interfering user and antenna I of the receiver. Okay. So, this is the channel coefficient of the this is the channel coefficient of the interfering user. And now, what we want to do in multi-user beamforming is something that is interesting. So, you have this multiple antenna system and that allows us to separate multiple users very interestingly to receive receive signal from the desired user while suppressing the interference from the interfering user as follows. So, we form a beam in the direction of the desired user, right. So, we form a beam, that is you maximize the signal gain in the direction of the desired user, right. Maximize gain in direction maximize the gain in the direction of the desired user, while in the direction of the interfering user there is no gain, that is gain equal to 0. So, there is a null in direction of there is a null in the direction of the interfering user. What this means is, that is the gain for the interfering user that is gain equal to 0 for the interfering user. So, this is your receiver. So, what this multi-user beamformer is doing is essentially there are two users, one is the desired. So, you want to receive the signal from one user, while you want to suppress the interference, the signal from the other user who is the interfering user. So, this multiple antenna system, it allows you to do that. It allows to direct your beam, the receive beam, that is maximize the signal gain in the direction of the desired user, while placing a null or zeroing the gain in the direction of the interfering user, so that the signal of the interferer is essentially suppressed, right. So, that is the essential. So, this is your null, this is known as null placement and so on, or interference suppression essentially, right. And therefore, the way this works is as follows. So, let us say we have the received signal, let us call this as y1, y2, yl, these are the outputs, and x1 is the transmit symbol of user 1, x2 is the transmit symbol of user 2. Then I can write this model as the system model for this multiple user system as y1, y2, yl, L is the number of antennas. This is the signal of the desired user, which is the channel coefficients h1, h2, hl times x1, the symbol transmitted by user 1, plus the channel coefficients of the interfering user g1, g2, gl times x2 plus n1, n2, nl, which is the noise vector, and therefore, this is y bar, this is equal to h bar, this is your channel vector g bar, this is n bar. So, we have y bar equal to h bar x1 plus g bar x2 plus n bar. This is the system model where y bar is the output vector, and this is your desired user channel. This is your undesired or interferer channel, and this is essentially your noise at the receiver, right. This is the receiver noise. Okay. Now, what needs to be done here is again, as we might have seen before, we perform beamforming. Remember, that is what we do whenever we want to perform the optimal signal processing, that is the maximize the signal to noise power ratio, and in this case maximize the signal to interference plus noise ratio. Maximize the signal to noise power ratio and also suppress the interference, right. So, maximize the SINR, that is what we are doing in this case, because there is also interference. So, our aim is to maximize SINR. What is SINR? This is the signal to interference plus noise ratio. We want to maximize the signal to interference plus noise ratio, right. And so, this is our aim. What is our aim? Our aim is to maximize the signal to interference plus noise ratio, and for that, and how do we do that? How to achieve this? How to achieve this? We ask the question how. Again, our answer is via good old beam forming, which is essentially nothing but the optimal combining. Right, this is nothing but optimal combining. So, take the received output symbols, and we perform W1 conjugate, W2 conjugate, so on, and we combine the output symbols, right. That is essentially we are performing W1 conjugate Y1 plus W2 conjugate Y2 plus WL conjugate Y1, which can be written as follows, and this is your vector W bar Hermitian, this is your vector Y bar, and these are essentially your combining weights, or these are essentially your beam forming. You can think of this as your beam forming weights, right. And therefore, I can write this as W bar Hermitian Y bar, where W bar is now, this is your W bar is the beam former that we seek. Okay. So, W bar Hermitian Y bar, this is the beam forming process, right. W bar is the beam former, this is your beam forming process. Okay. And so, therefore, we are combining the outputs Y1, Y2, YL across the antennas using the weights W1, W2, WL, and if we denote this by the vector W bar, we want, that is essentially what is our optimal combiner, or this is our optimal this is the beam former, right, because essentially we are trying to find a beam, that is essentially what the beam former means, and this vector W bar is the beam forming vector, and we wish to find the optimal beam forming vector, which essentially maximizes the signal to interference plus noise ratio. Okay. So, that is the aim. So, your W bar equals W1, W2, WL. Okay. So, and this is your beam former. Okay. And now, how to choose the beam former? Now, the question that we want to ask is how to choose the beam former. How does one choose the beam former? And the solution to that is the following thing. we want to perform W bar Hermitian y bar, which is substituting for y bar is nothing but h bar. If you go back and take a look at this is h bar times x1 plus g bar times x2 which is equal to W bar Hermitian h bar times x1 plus W bar Hermitian g bar times x2 plus W bar Hermitian times n bar, and now there are three components. One is the desired signal, the other is the interference, and this is the noise. Okay. And we want to maximize the signal to interference plus noise ratio. What we will do is we will start with the desired signal. For the desired signal, what we are going to do is we are going to set W bar Hermitian h bar equal to 1. So, this implies that the gain of the desired signal equals unity. Okay. So, we are fixing the gain of the desired signal to be unity. And then now the other important condition here is essentially what happens to the interference. Remember, we want to suppress the interference, we want to place a null, that is we want to reduce the interference to 0, which means this second quantity W bar Hermitian g bar, this must be equal to 0. That is, if you look at this quantity W bar Hermitian g bar, that is W bar Hermitian g bar, this must be equal to 0, right, for this is the gain of interference. Okay. Now, by setting it equal to 0, what you are doing is you are suppressing the interference, right. W bar Hermitian g bar equal to 0, you are suppressing the interference, and therefore, now you put these two things together, you have, or let me write it slightly differently, you have h bar Hermitian W bar equal to 1, taking the Hermitian of that, and you have g bar Hermitian W bar equal to 0, which implies, now putting this together as a matrix, you have h bar Hermitian and g bar Hermitian times W bar equal to 0, and this is a basically this is a 2 cross L matrix, and let us call this matrix as C Hermitian. Okay. So, this implies that we have from these two conditions, you have C Hermitian W bar, I am sorry, this has to be equal to 1 0, because h bar Hermitian W bar equal to 1, g bar Hermitian W bar equal to 0. So, this is equal to 1, this is equal to 1 0, where what is the matrix C? C Hermitian, remember, is h bar Hermitian g bar Hermitian, which implies C, if you look at C, the matrix C is the desired channel vector of desired user, channel vector of interfering user. So, this is going to be your L cross 2 matrix of size L cross 2. What is H bar? H bar is desired user channel, and this is your interfering user, interferer channel. desired user channel, and then you have the interferer channel. Okay. And therefore, we have once again C Hermitian W bar equal to 1 0. This is our constraint. And you can see if C is C Hermitian is of size 2 cross L, which means if L is greater than 2, that is number of antennas implies this becomes a wide matrix. For number of antennas greater than 2, this implies wide matrix, which implies this becomes your underdetermined system. Okay. So, for L greater than 2, that is when you have number of antennas greater than 2 at the receiver, you have 4, 3, 4, 5 and so on, right. This becomes an underdetermined system. To constrain the solution, now of course, we have another aspect, that is the noise power. Turns out that the noise power, now if you look at the output noise power, recall the noise is basically, if you look at this, if you go back and take a look at this, this is our W bar Hermitian N bar, that is your noise power, right. So, that is your noise power. So, the noise is W bar Hermitian N bar, and turns out that the noise power is proportional to norm of W bar square. So, essentially the pertinent optimization problem for this multi-user beamforming, that can be formulated as minimize the noise power, right, minimize noise power. So, the relevant optimization problem is minimize norm W bar square subject to the constraint C Hermitian W bar equals this quantity, that is 1 comma 0, right, and this is now essentially, so this is basically minimize the noise power, minimize the noise power. This is desired signal gain. This is your interference. This is essentially your and therefore, this if you look at it, this multi-user beamforming problem, this is now your, this is now a minimum norm problem, all right. That is a minimum norm or the least norm problem, all right. So, you can also, I mean it is the same thing, this is the least norm, this is the least norm problem. And therefore, the only difference here is that you have A equal to C Hermitian, and the solution therefore is given as, remember the solution was A transpose, but for complex matrix you can replace the transpose by Hermitian. So, this become 8 Hermitian A Hermitian inverse times y bar, which is in this case 1 comma 0. So, this is your vector y bar. Now, replacing A by C Hermitian, this becomes C Hermitian C inverse 1 comma 0, and this is basically your desired multi-user beamformer. So, the optimal multi-user beamformer is C C Hermitian C inverse 1 comma 0. So, this is your essentially your this is basically the multi-user beamformer. Okay. And what is this beamformer doing? Fixing the signal gain, minimizing the noise power. So, it is basically maximizing the SNR, signal noise power ratio. At the same time, interference is 0. So, you can say that it is maximizing the signal to interference plus noise ratio, because interference plus noise is simply the noise, right. So, if you look at SINR, that is essentially your signal power by interference power plus noise power. Now, in this formulation our interference power, this is equal to 0. So, this reduces to signal power by noise power. Now, the signal power, the signal gain equal to unity, which means this is a constant divided by, what we are doing is we are making constant signal power. So, signal power is constant and we are minimizing the noise power. So, this maximizes the SNR, which in terms maximizes the SINR, because as I have already told you the interference power is 0. So, maximizing the signal power, signal to noise power ratio is simply the same as maximizing the signal to interference plus noise ratio. Okay. So, this is W bar. You can think of this as the optimal multi-user beamformer. This is the optimal multi-user beamformer. Optimal MU, that is multi-user beamformer. That is what your W bar is. As usual, let us do a simple example to understand this. Simple example, let us say you have given a problem in which your H bar is 1 1 1 1 and your G bar, that is the interference channel, is 4 2 2 4, right. And one can ask the question, what is the optimal multi-user beamformer W bar? For that, you first form the matrix C, which is H bar G bar, which is essentially your matrix 1 1 1 1 4 2 2 4, right. And remember, using the expression W bar equals C Hermitian C inverse 1 0. So, let us first form C Hermitian C, that is 1 1 1 1 2 4 2 2 4. C Hermitian times C, that is 1 1 1 1 4 2 2 4, which is equal to 4 40 12 12, and therefore, C Hermitian C inverse, this is equal to 40 into 4 160 minus 12 into 12 144, that is 1 over the determinant, which is 16. Once again, now we are very familiar with this, computing the inverse of 2 cross 2 matrix. Switch the diagonal elements, negative of the off diagonal elements. This is C Hermitian C inverse, and therefore W bar optimal, which is equal to C, which is essentially your what is this? This is your matrix 1 1 1 1 4 2 2 4 times 1 over 16 40 minus 12 minus 12 4 times the vector 1 comma 0, which is essentially, now if you look at it, this is 1 over 16 1 1 1 1 4 2 2 4 times 40 minus 12, which is essentially, if you divide by 4, 1 over 4, this will be 1 1 1 1 4 2 2 4, this will be 10 minus 3, and you can evaluate this. It is not very difficult to see. Your W bar reduces to 10 minus 12 divided, that is minus 2 divided by 4, that is minus half. 10 minus 6 4 divided by 4 1, and once again 10 minus 12, that is minus 2 divided by 4, that is minus half. So, the optimal beamformer W bar for this system that maximizes the SINR is essentially minus half 1 1 minus half. Okay, and this essentially is the optimal, this essentially is your optimal beamformer. What is it doing? Signal gain is constant, interference is 0, minimizing the noise power, therefore maximizing the signal to noise power ratio, at the same time maximizing also the signal to interference plus noise ratio. All right. So, this is an very interesting application. In fact, one of the most profound applications of least norm. You can see it is a very practical application in a multi-user system where you want to maximize the gain of the desired signal, but at the same time suppress the interference, right. So, this can therefore have very interesting and very important applications in wireless communication. In fact, you can easily extend it to a scenario with more than 2 users. It is not very difficult to see how you can maximize the signal gain of a desired user while minimizing the interference caused by more than 1 users, 2, 3 and so on. And I urge you, right, to think about this, right, how would you extend this to a scenario with more than 1 interfering user. All right. So, with that, let us stop this module here and let us continue in the subsequent modules. Thank you very much.